Welcome back to the Business Enhancement Series presented by Efficiency United and Semco Energy Gas Company. This next section is going to focus on the basics of financing. We'll start with some key financial terminology. So first, simple payback period, often abbreviated SPP or actually even SPB. That's how quickly the cost of implementing a measure is recovered from the savings. Asked another way, how quickly will the savings cover the product's purchase price? The calculation of simple payback can determine at what point this will occur through the realized savings. So you take the investment, the total investment, and then divide it by the amount you're saving. If it's a monthly saving, a quarterly savings, that will tell you the number of that time period that it'll take in order to pay it off. So here's an example. A family is replacing the air conditioning unit at their home and is considering the following options. You've got the base unit. A minimally efficient 13 SEER unit costs $1,850 and it'll consume just under 7,500 kilowatt hours per year. Then you've got option 1. It's a 15 SEER rated unit cost at $2,250 after rebate of $200. And it'll use just under 6,500 kilowatt hours a year. And then the other option is a 17 SEER unit, costs $2,950 after rebate, and will consume just over 5,700 kilowatt hours a year. So which investment over the minimum requirement is recouped faster? Well, we need to calculate the savings. So let's determine the cost savings of option 1 versus the base. So at 7,477 kilowatt hours a year minus 6,480 kilowatt hours a year, multiplied by 10 cents, the cost of a kilowatt hour, the savings is about $99.69 a year. So that means in this case that the SPP, the simple payback period, is 4 years. Now let's look at option 2. Again, it's the cost saved equals the annual energy of the base minus the annual energy of option 2 times the cost of the actual energy. So 7,477 kilowatt hours a year minus 5,718 times the 10 cents is $175.93 per year. So again, the simple payback period to recoup the actual cost is 6.3 years. You save more per year, but it doesn't necessarily offset the cost increase. So now we get to compare 4 years versus 6.3 years. Which option would you choose? Why would you choose it? There are certainly reasons to use both, and the answers might vary. So SPP criteria depends on when you need the money back for other things. A homeowner's criteria will likely be very different from that of a business owner. A homeowner can accept a longer payback. The SPP of a homeowner project might be longer, sometimes maybe even 15, 20 years. Businesses tend to want SPPs in the 2 to 4 year period. Another key financial term, initial return on investment, or ROI. For energy projects, ROI is the savings earned on an investment as a percentage of the investment. So a different way to look at cost savings. Your return on investment is your savings divided by the investment. This might be compared to looking at bank interest or stock earnings. Businesses are typically weighing multiple options, and this can help determine where they want to invest their dollars. So here's another example. An entrepreneur is replacing the central air conditioning at their office and is considering the following options. We have the same options, the base at $13 and $18.50. Option 1, $15 and $22.50. Option 2 is the 17 SEER unit at $29.50. So then we look at the investment and the savings. Now, in this case, we're looking at the investment as the additional cost from the base option. So your cost is $400 for option 1, savings per year of $99.69, and that represents 25% of the total increase of the investment. Option 2, savings divided by investment, $175 a year, but $1,100 additional cost, and that represents 16% of the total investment. You come up with a very similar answer, and your reasoning is the same. You go with option 1. So let's talk about evaluating the use of the SPP and the ROI. So some of the advantages of this method, well, it's simple, easy numbers, it's fast, and it gives you a metric for risk. Some of the disadvantages, well, it ignores the time value of money. It ignores cash flow. So you potentially are holding up a bunch of cash in an investment that you make that you have to pay back over time. It automatically assumes that your savings are going to be consistent over the entire life of what you're talking about. It ignores lost opportunity costs to the do-nothing response. And it ignores the total cost of ownership, that is, maintenance, bills. It only talks about savings in relation to the investment. So then we talk about return on investment versus simple payback period. Even a longer SPP, which many business owners don't like, there's still a payoff. If you could get a 10% or 5% payout, would you still invest? What can you currently get at the bank or in the stock market? So at a 16%, that may be highly desirable as a payback for investing your funds as opposed to even a more traditional investment. The next term to talk about is life cycle cost, LCC. And that's going to include all sorts of things: the design, the installation, the financing of actually purchasing the product, the operation of it, so you have energy, you have water cost, maintenance, so corrective, preventative, predictive maintenance. Then you have the decommissioning of it, however many years down the road, and that can involve resale, it can involve salvage, or straight up disposal. So a lot of different things are involved. So life cycle costs can actually be more appropriate than SPP or ROI for high-ticket upgrades like HVAC and windows. This is largely used for business owners, but as homeowners get more sophisticated with computer programs and apps, they start to consider this type of model as well. Another term, present value. The present value of future cash flows. That considers the time, the value of money due to interest and inflation. So we have a slightly more complicated equation. So you take the future value and divide it by 1 plus the interest per time period multiplied by the factor of n, which is the time periods between present and future. So the time value of money, seeing as money tomorrow is not what it is today because it can earn interest, if the money isn't at least keeping up with inflation, it is of lesser value. This helps to determine whether it's better to invest the money or to invest in the upgrade. So let's apply real numbers. An energy manager plans to purchase a replacement boiler in 5 years. The cost today is $75,000. If the annual inflation rate is 2.2%, what's the boiler going to cost in 5 years? So we have the present value, the future value, divided by 1 plus the interest to the factor of the time period. $75,000 is our present value. Our interest rate is 2.2%, and the time period is 5 years, which means the future value of that $75,000 is $83,621, which means what costs you $75,000 today in 5 years is going to cost you $83,621. So calculating the time value of money can definitely be done in simpler ways, handy tables where you actually go across for your interest rate, go down for the number of time periods, years, and you take that multiplier and apply it back to that formula that we talked about. So now we got to speak TVM, speak the time value of money. So here's our equation, A divided by B at I over N periods, right? So A is the unknown quantity, B is the known quantity, I is the known discount, the interest rate, and N is the total number of periods. Discount comes from the fact that money tomorrow doesn't have the same purchasing power of money today. So it's actually reduced. It's not the good kind of discount. So let's go back to that example, and we'll call this version example 4. That entrepreneur is replacing the central AC at their office and is considering these following options. So we know the base is that 13 SEER unit cost at $1,850. We know option 2 and option 3. So all models have an expected life of 15 years. So with an installation cost of $2,000 across the board, a salvage value of $100, and a maintenance contract worth $150 a year, the annual rate of inflation is 3%. So now all of a sudden we're looking at the total cost over the total life of the unit. Which is a better investment now? Well, first we determine the present value factor for the operation and maintenance costs. So we go ahead and use one of our tables, and we're going to come up with a number. Now, there might be some differences based on different tables, but they vary very slightly and not significantly. Then we have to determine the present value factor for the future salvage cost. We'll get that from a table as well. So step 3 is to determine the life cycle cost for each option. So we've got the acquisition cost, in the base example, $1,850, plus the cost of installation, $2,000. And then we have the operation and maintenance costs. And then we're going to add back in the salvage cost. But as you can see, multiplied by 0.64 based on the loss of value of money. So now you have a total life cost of $14,502, $13,712, and $13,502. Now all of a sudden, option 2 is the best deal. Over the total life of the equipment, it's going to cost the least amount by about $1,000. So now we go back and look at our different analysis methods. So we have the simple payback period. Option 1 was the best deal. Return on investment, again, option 1. But over the life cycle of the equipment, option 2 ended up being the best deal. Illustrating these can actually help you make a better sale for both you and the customer. Depending on the customer's true economic needs, quick turnaround, long-term value, they might make a choice they might later regret. If money's a real issue, the complete economic analysis should be done before making decisions about the upfront costs. Some other things to think about when in regards to life cycle cost. Different equipment may have different useful lives. A common study period must be selected for all the measures. So you've got the options, the shortest life, the longest life, the least common multiple life, or then just arbitrary. And the same interest rate must be used for all the alternatives you're looking at. So in short, the shortest life of the options being considered, if a product has a life of 5 years and the other has a life of 7 years, you'd choose 5 years. Longest life of the options being considered, if the product has 5 years and the other a life of 7 years, you'd choose 7 years. And then the least common multiplier of the options being considered is if the product has a life of 5 and the other has a life of 7, you choose 35 years and assume additional equipment needs to be purchased. Arbitrary is still arbitrary, but using the same interest rate for all the alternatives will allow us to come back and use this as a comparison. What about depreciation? So depreciation is not a cash flow. Depreciation is a business expense, and it actually lowers taxable income. A lower taxable income means lower taxes, and taxes are a cash flow. Now, to come up with a life cycle cost that's acceptable, can we make this process simpler? Well, yeah. With a simplified life cycle cost, we take the investment minus the salvage value plus the life expectancy times the annual costs. It actually gives us numbers fairly close to what we came up with before, and it's certainly a lot faster. And option 2, still head over heels above the rest. How about this term? Minimum attractive rate of return, MARR, a company-specific value used to evaluate projects. So if the project has a rate of return greater or equal to the MARR, it's considered a viable project. Business owners are definitely going to be more interested in this term. Some businesses might call this the hurdle rate. Your MARR is going to vary based on a lot of different issues, definitely financing. And MARR, when you're talking about debt capital, is typically higher than that for equity capital. So let's look at another example. An energy manager has $4,300 available to invest in the high efficiency air conditioner. Her company has an MARR of 10%. So what savings is needed each year to justify the project? So you know the budget, the P. You know the interest, the 10%, which is what they could do if they didn't do the project. So what savings each year is needed in order for the project to be justified? They need to save $565.54 a year. So would the manager consider this a viable project based on the numbers? Well, let's look at example 7. The energy manager of a small office building, considering the replacement of her HVAC and building control system. The project's going to cost $100,000, and it'll save 225,000 kilowatt hours a year for 10 years. So the company uses an MARR of 10% and pays 8 cents per kilowatt hour. Would the manager consider this a viable project? So let's look at the numbers. We know our cost, $100,000. We know the company's 10% MARR, which we'll call our interest. And then using the table, we come up with the multiplier of 0.1628. So the minimum annual savings is the $100,000 times the 0.1628. That gives us $16,280. That's how much the money is worth to them if they don't do it. Now we look at the amount saved. 225,000 kilowatt hours a year at 8 cents comes out to $18,000 a year. What does that mean? Well, it means the acceptable annual savings is $16,280 and the actual savings are $18,000. You want the actual savings to be higher than the acceptable. And yes, this is a viable project. Another term, opportunity cost. So opportunity cost is the benefits lost when dollars are not invested. Energy Star is a voluntary partnership between organizations, businesses, consumers, and government united in the pursuit of a common goal to protect our environment for future generations by changing to energy efficiency products and practices today. If one doesn't do an energy project, one still pays for it in terms of higher costs. If you're going to pay for it anyways, you might as well do it. This is a term that can help encourage an indecisive or an unsure customer. Basically, this is what I'm paying now. This is what you could be paying. The U.S. Department of Energy developed a tool online to help decision makers quantify the cost of delaying energy project implementation. Basically, how much money are you throwing away by waiting? This helps you answer how much new equipment might be purchased from anticipated savings from upgrading. It'll also help them decide whether the purchase should be financed or they should wait for the cash. And also it'll tell you whether money's being lost by waiting for a lower interest rate. Very helpful tool that you can help direct your customers to. Final example in this section. A customer is undertaking a major building upgrade and installing the following items: new HVAC equipment, new water heating equipment, controls, air sealing, insulation, and windows. So the total cost after applying Efficiency United utility rebates is $75,000. The annual energy savings results in an anticipated simple payback period of 5 years, 4 months. All right? You've assisted the customer in finding financing at 6% for 7 years. The customer thinks they can qualify for a better rate, 4% next year. So how long before the energy savings lost from waiting to do the project erodes the benefit of the lower interest rate? Well, you can just plug it right into the table. The initial interest rate is 6%, and the customer's wanting to wait for a better rate of 4.9%. Putting that data into the software along with the project costs of $75,000 with a simple payback period of 5 years and 4 months and a loan term of 7 years. So we can see that by waiting, the customer loses out on potential savings of $1,200 per month. We can see that after 4 months, the lost savings outweighs the gains of having a lower interest rate. Well, this section certainly had a lot of numbers. The next section, we're going to talk about funding instruments for energy projects. How do you get the money? As the Business Enhancement series presented by Efficiency United and Semco Energy Gas Company continues. Click the next section titled Funding Instruments for Energy Projects.